Color coding. A color code is used to help electricians identify wire by the color of the insulation. When you can quickly identify the wire by color, it's easier to properly install and connect the wires. The code book does not have a set color coding for wires. It does stipulate that neutral wires, grounded wires, will be white or gray, or any color other than green with a white stripe or 3 white stripes. The grounding conductor has to be green or bare or green with a continuous yellow stripe. So it has stipulated green and white and gray. We cannot use those for ungrounded conductors. We can use any other colors. So we can use black, red, blue, brown, orange, yellow, purple, magenta. But there's a rule of thumb in the electrical trade that low voltage, and I mean 120, 240, 120 volt, 240 volt, we use black, red, blue. If it's a higher voltage of 240, 480, we use brown, orange, yellow. So you'll get used to those different designations of color coding. So a typical color code is as follows. 2 conductors will be black, white, and a green. 1 white or gray, 1 black wire, and an equipment grounding conductor. 3 conductor cable, and this is highlighted, will be black, red, white, and green. So 1 white or gray, 1 black wire, 1 red wire, and an equipment grounding conductor. So it's black, white, ground, black, red, white, ground. 4 conductor cable, you won't see this in residential because they say it's a 3-phase conductor or cable. It's black, red, blue, white, and ground. So same as 3 conductor cable plus a 4th wire, blue. 5 conductors, same as the 4 conductor cable plus a 5th wire, yellow. Here's a highlight. It says the equipment grounding conductor may be bare, green, or green with a yellow stripe. So here is their breakdown. So 2 conductor, you have black and white. 3 conductor, you have black, red, white, or gray. 4 conductor, you have black, red, blue, and white, or gray. And 5 conductor, you have black, red, blue, yellow, and white, or gray. Ungrounded conductors can be any color except white, gray, or green. However, it's a good practice to color code conductors. In fact, many construction specifications require color coding. Furthermore, on a 4-wire delta connected secondary, where the midpoint of one phase winding is grounded to supply lighting and similar loads, the phase conductor having the higher voltage to ground must be identified by an outer finish that is orange in color. They call that the high leg or the stinger leg. That high leg has to have an outer finish that is orange. These types of identification must be placed at each point where a connection is made if the grounded conductor is also present. Warning, the higher voltage phase conductor is typically 208 volts to ground, where the other 2 phases would be 120 volts to ground. Only use the higher voltage phase as part of a 3-phase load that does not use the neutral conductor as part of the load. If you accidentally put a circuit breaker on the B phase of a 3-phase panel, if it's delta, you're going to have a receptacle that has 208 volts instead of 120 volts, and you could burn stuff up. 1.4.6 wire rating. A critical factor in selecting the correct conductor is its maximum operating temperature. Another important consideration is where the conductor will be terminated. The temperature rating of the termination may limit the allowable ampacity of the conductor. So NEC Table 310.4 shows the conductors have various temperature ratings. Since Table 310, 16, and 17 are based on an assumed ambient or surrounding temperature of 30 degrees Celsius, conductor ampacities are based on the ambient temperature plus the heat, the I squared R, produced by the conductor while carrying current. Therefore, the type of insulation used on the conductor is the first consideration in determining the maximum permitted conductor ampacity. For example, a number 3/0 THW copper conductor for use in a raceway has an ampacity of 200 amps, according to table 310.16. In a 30 degrees Celsius ambient temperature, the conductor is subjected to this temperature when it's carrying no current. Since a THW insulated conductor is rated at 167 degrees Fahrenheit or 75 degrees Celsius, this leaves a wide margin for increased temperature due to current flow. If the ambient temperature exceeds 30 degrees Celsius, the conductor maximum load current carrying rating must be reduced proportionally so that the total temperature won't exceed the insulation's temperature rating. For the same reason, the allowable ampacity must be reduced when more than 3 current carrying conductors are contained in a raceway or cable. Again, it's about heat dissipation. We want the wires to be able to dissipate that heat. The heat isn't going to bother the copper. Copper is copper. So if you have a wire that's good for 90 degrees Celsius and it's copper, or you have a wire that's rated for 60 degrees Celsius copper, that copper is the same copper. It's the insulation that makes it good for 60 degrees Celsius or 75 degrees Celsius or 90 degrees Celsius. If you have a 60 degrees Celsius rated wire and you're putting 90 degrees Celsius of temperature on it, that insulation is going to bake. It's going to become brittle. It'll harden. And over time, that insulation is going to crack and it'll fall off the wire so that now we no longer have an insulated conductor. We have a bare copper wire with current running through it. That's a very dangerous situation to be in. It's likely that it'll short out against something metal, and if not, it's likely that someone will get hurt when they come into contact with it. So we want to make sure that we protect the insulation of the wire by limiting the amount of current flow through the wire to keep the temperature rating below that of the rating of the insulation of the wire. As part of the wire rating, when you select a conductor, you must consider the maximum operating temperature. Some things that affect a conductor's operating temperature are the ambient temperature, that's the air around us, the current flow in the conductor, including harmonic currents, the current flow in bundled conductors, which raises the ambient temperature, and how the rate at which heat dissipates into the surrounding medium is affected by the conductor insulation. Factors that affect the amount of current a conductor can carry safely at the maximum safe temperature the conductor can reach include the conductor size, which is the diameter in circular mills, the ambient temperature, the number of conductors in a bundle, the cables installed in contact with thermal insulation, and where you install the conductors such as raceway, conduit, ducts, or underground. Fixture wiring. Fixture wire is used for interior wiring of fixtures and for wiring fixtures to a power source. Guidelines concerning fixture wire are given in Article 402. The list of approved types of fixture wire is given in Table 402.3. Figure 8 shows an example of fixture wire. The wires are composed of insulated conductors with or without an outer jacket. Conductors range in size from number 18 to number 10. So here's a transparent outer jacket. You can't use fixture wire for building wire. What I mean by that is you cannot use fixture wire to extend a receptacle in a wall. Fixture wire is just that. It's for wiring of a lighting fixture. To select a fixture wire, you must consider the fixture's operating temperature. The wire must have the right insulation for the temperature. For example, If you had a fixture with a maximum operating temperature of 250 degrees Celsius, you'd select fixture wires insulated with perfluoric, I'm not going to pronounce it, PFA, or extruded poly, I'm still not going to. This is the highest operating temperature allowed for any fixture wire. That's a high rating of wire, 250 degrees Celsius. As indicated by NEC section 402.3, fixture wires are suitable for service at 600 volts unless otherwise specified in table 402.3. The allowed ampacity of fixture wires are given in NEC table 402.5. Here's a highlight. It says, although the primary use for fixture wire is the internal wiring of fixtures, several of the wires listed in table 402.3 may be used for wiring remote control, signaling, or power limited circuits in accordance with NEC section 724.49. Fixture wires may never be used as a substitute for branch circuit conductors. 1.6.0 Cable types and applications. Cables are two or more insulated wires and may contain a grounding wire covered by an outer jacket or sheath. National Electrical Code requires that all cables and associated fittings be listed. Cables usually classified by the type of covering it has, either non-metallic or metallic. Metallic covered cable is also known as armored cable. Cable may also be classified according to where it can be used. NEC table 400.4. Because water is such a good conductor of electricity, moisture on conductors can cause power loss or short circuits. For this reason, cables are classified for dry, damp, or wet locations. Cables can also be classified regarding exposure to sunlight and rough use. There are two factors to be considered when determining the type of cable to be used for a specific application: type of conductor insulation and the cable jacket. Both must be appropriate for the application. All cables are marked to show important properties and uses. Cable markings show the wire size, the number of conductors, cable type, the voltage rating. A marking may also be included that indicates the approved service or application. This information is printed on metallic cable. Marking information is usually included on a tag. So here's type NM. It's non-metallic sheathed cable. This is what we usually call Romex. That's the cable type. It's good for 600 volts. The wire size is 14 gauge. There are two current carrying conductors in the sheath with a ground. So that's the black and the white and the bare ground. And then this is a plastic thermoset sheath that surrounds it. Here's your Romex or your non-metallic sheath cable. 14.2 with ground type NMB, 600 volts. 1.6.1 non-metallic sheath cable. Non-metallic sheath cable is widely used for branch circuits and feeders in residential and commercial systems. Both types are commonly called Romex, even though the cable manufacturer only refers to type NM as Romex. So non-metallic sheath cable. This cable consists of two or more insulated conductors and one bare conductor enclosed in a non-metallic sheath. The conductors may be wrapped individually with paper, and the space between the conductors may be filled with jute, paper, or other material to protect the conductors and help the cable keep its shape. The sheath covering both type NM cable and NMC cable is flame retardant and moisture resistant. The sheath covering type NMC has the additional characteristics of being fungus resistant and corrosion resistant. All right, that is a highlight. NEC Article 334 lists the allowed and prohibited uses of type NM and NMC cable. Both can be installed in either exposed or concealed work. The primary difference is that type NM cable is suitable for dry locations only, while type NMC cable is permitted for dry, moist, damp, or corrosive locations. Type NM and NMC cables may be used in one-family, two-family dwellings, and in certain multifamily dwellings depending on the type of construction. Type NM and NMC cables cannot be used in the following situations: in ducts or plenums where toxic gases from burning cable insulation could be spread throughout the structure, installed exposed in the space above suspended ceilings other than in one-family, two-family, and multifamily dwellings, as service entrance cable embedded in concrete or in hazardous locations. There are many other requirements for types NM and NMC cables specified in Article 334. Before installing this type of cable, be sure you read and understand the applicable sections of the NEC. 1.6.2 Underground feeder and branch circuit cables. Guidelines for the use of underground feeder and branch circuit cable are provided in NEC Article 340. Type UF cable is similar in appearance, construction, and use to type NMC cable. The primary difference between these two cables is that type UF cable is suitable for direct burial, but type NMC is not. Refer to Article 340 for specifics on where and when to use type UF cable. Figure 11 also lists basic guidelines for using type UF cable. So you're allowed to use UF cable underground and direct buried, as a single conductor cable, as non-metallic sheathed cable, in solar photovoltaic systems, in cable trays, in wet, dry, or corrosive conditions. You're not allowed to use UF cable as service entrance cable in commercial garages, in theaters and similar locations, in storage battery rooms, in hazardous locations, in hoistways, elevators, or escalators, embedded in poured concrete, cement, or aggregate, exposed to sunlight unless designed for that use, overhead cables, and where subject to physical damage. 1.6.3 Medium voltage cable. Medium voltage cable is covered in Article 315. Type MV cable consists of one or more insulated conductors encased in an outer jacket. This cable is suitable for use with voltages ranging from 2001 volts to 35,000 volts. It can be installed in wet and dry locations and may be buried directly in the earth when rated for such use. Refer to Figure 12. So, here's medium voltage cable. And notice how medium voltage is 2001 volts up to 35,000 volts. So here's the jacket. Here's a copper tape shield, and it has insulation semiconductor. Then here's the EPR insulation, and then there's finally the copper conductor itself. This insulating semiconductor helps with stray voltages or helps with the accumulation of static voltage on the insulation of the conductor. And this copper tape shield will take any of the buildup of static electricity, it'll take it to ground. When you're terminating this type of cable, you take the copper tape shield and it's taken to ground. And it keeps it from blowing out the cable in other places. It bleeds off that excess induced voltage in the cable jacket. It takes it to ground. 1.6.4 Metal-Clad Cable. Metal-Clad type MC cable, that's highlighted, consists of one or more insulated conductors encased in a metal tape or a metallic sheath. NEC Article 330 covers type MC cable. Further information can be found in UL 1569 standard for metal-clad cables. Type MC cables used in a wide variety of applications, from small instrumentation cable up to medium voltage feeders. The conductors are coated with a thermoset or thermoplastic insulation. Type MC cable can also be a composite of electrical conductors and optical fiber conductors. Type MC cable is available in several configurations with or without an outer jacket. One example of type MC cable is shown in Figure 13. So it has this aluminum spiral wrap or corrugated extruded outer sheath, and that protects the conductors inside. And then if it's going to be outdoors, they'll also put this plastic thermoset covering over the whole thing, and that protects it from moisture. Type MC cable is a type of cable that is widely used in both commercial and industrial environments. It's available in many configurations with or without an outer jacket. Some of the special applications for MC cable include home run cables, super neutrals, direct burial, and fire alarm cable. Markings on type MC cable include the maximum rated voltage, gauge size or circular mill area, and the insulation type. Cables with special uses are marked accordingly. The outer covering may be of non-metallic jacket over the metal sheath. If the outer covering cannot be marked, the marking will be on a tape inside the cable along the entire length of the cable. If on the outside, the markings typically have a 24-inch spacing. Following are three types of MC cables: smooth metallic sheath, corrugated metallic sheath, and interlocking metal tape armor. Uses for MC cable are specified in NEC section 330.10. These include the following: services, feeders, branch circuits, power, lighting control, and signaling circuits, indoors and outdoors, exposed or concealed, direct buried if identified for the use, and in any raceway non-metallic type. Applications where type MC cable cannot be used are specified in section 330.12. These include the following: it cannot be used in corrosive or damaging conditions unless the outer covering protects the conductors or some other protective material is used. Cannot be used in areas where the cable is subject to being physically damaged. Cannot be used in direct burial with the earth or in concrete unless it's identified as direct burial or where subject to caustic materials. Both armored clad cable and MC cable provide advantages during installation. Flexible metal sheath protects the conductors and allows them to bend around corners without kinking or damaging the conductors. Other advantages of metal-clad cables are their relative ease, easy installation without the need for wire pull or fish tape or lubricant. A fish tape is a hand device used to pull wire through a conduit run. Table 3, differences between types AC and MC cable. Type AC has a maximum of 4 conductors plus an equipment grounding conductor. Type MC, there's no limitation to the number of conductors and sizes, sized from 18 gauge to 2000 kc mil. Armored cable includes an interior bonding strip. This strip is in constant contact with the armor and with the armor forms an equipment grounding conductor. Type MC cable does not include a bonding strip. MC cladding is not an equipment grounding conductor, although it can supplement the equipment grounding conductor. Uses moisture-resistant and fire-retardant paper wraps on individual conductors. Type MC cable does not have a paper wrap, but incorporates a polyester tape used on the assembly. Okay, 1.6.5, high voltage shielded cable. Shielding is added to high voltage cables for protection. It protects the conductor's assembly against surface discharge or burning due to corona discharge in ionized air. Without the shielding, the insulation and jacketing could be damaged or destroyed. So at these higher voltages, it said there's a coronal effect that's going to actually build up a static charge, much like a capacitor. And we don't want that to happen because it can get too much to where it'll actually damage the insulation. It'll blow a hole through the insulation of the wire, and then the wire will be no good. So we take that buildup, that coronal static layer, and we take it to ground with this copper shielding tape. There's a semiconductor shielding of non-metallic tape wrap. Then there's the cross-linked polyethylene insulation or other insulation. And then there's finally one last semiconductive strand shielding. And here's your conductor of copper or aluminum. When you're terminating this, you have to be very careful and skin these separate layers out individually. And this last layer, when you take this semiconductive material off of the copper or aluminum, you have to use sandpaper or burnishing cloth to try to get any residue from the semiconductor off of the copper. You don't want it to track back. You especially need to clean this insulator for the same reason. Might have some semiconductive material on it that will allow those stray voltages to track back and try to get to ground. And it may cause the high voltage to jump to ground rather than staying contained in the system. It'll blow out. 1.6.6 channel wire assemblies. Channel wire assemblies comprise an entire wiring system which includes the cable supports, splicers, circuit taps, fixture hangers, and fittings. Figure 15. Guidelines for the use of the system are given in NEC Article 322. So it's a lot like Unistrut in that it's a metal box, and inside the metal box they have the conductors insulated from the metal. And then when you want to put one of these trolleys in, you can see these two prongs will tap into the neutral and one of the hots. There's four conductor channel. It'll tap into the ones that it needs, and you'll be able to put lighting fixtures on this. It has different taps. It has a terminal block where you can bring the power to it. Flat cable assemblies consist of 3 or 4 parallel number 10 special stranded copper conductors. The assemblies are installed in an approved U-channel surface metal raceway with one side open. Tap devices can be inserted anywhere along the run. Connections from the tap devices to the flat cable assembly are made by pin-type contacts when the tap devices are fastened in place. Pin-type contacts penetrate the insulation of the cable assembly and contact the multi-stranded conductors in the matched phase sequence. So these pins will tap into whichever ones of these they need. And these are 3 phases like A, B, C, maybe black, red, blue. And this is your neutral conductor. And then the very shell itself is the ground. As indicated in section 322.10, the wiring system is suitable for branch circuits that only supply small appliances or small power loads. It's suitable for exposed wiring only and may not be concealed within the building structure. This cable is ideal for quick branch circuit wiring at field installations. 1.6.7 Flat conductor cable. Flat conductor cable comprises an entire branch wiring system similar in many respects to type FC assemblies. The main advantage of the system is that it's the ease of installation. It's the ideal wiring system for use when remodeling or expanding existing office facilities. Guidelines for the use of this system are given in Article 324. Type FCC cable consists of 3 to 5 flat conductors, one of which must be an equipment grounding conductor placed edge to edge, separated and enclosed in a moisture-resistant and flame-retardant insulating assembly. Accessories include cable connectors, terminators, power source adapters, and receptacles. This wiring system is designed to supply floor outlets in office areas and other commercial and institutional interiors. It's meant to be run under carpets so that no flooring drilling is required. Carpet squares no larger than 1 meter square that are adhered to the floor must be attached with release type adhesive. It's also suitable for wall mounting as indicated in 324.42b. Telephone and other telecommunications circuits may share the same enclosure as type FCC cable. One 1.6.8 Power and Control Tray Cables. Guidelines for using power and control tray cables are provided in NEC Article 336. As the T in the letter designator indicates, this is tray cable and can be used in cable trays and raceways. It may be buried directly if the sheathing material is suitable for the use when indicated by the cable marking Type TC cable is also good for use in sunlight. Type TC cable consists of 2 or more insulated conductors with or without associated bare or fully insulated equipment grounding conductors and covered with a non-metallic jacket. The cable is listed in conductor sizes from number 14 gauge to 1000 kc mil for copper, or number 12 gauge to 1000 kc mil for aluminum or copper-clad aluminum. Type TCER, tray cable exposed run cable identified as joist pull, may be used in 1 and 2 family dwellings and pulled through framing members. Is that TCER? So you've got 3 conductors. They're actually numbered 1, 2, and 3, and one of those can be a neutral. It looks to me like they've got a bare neutral and they've got grounds. They're saying that's called the binder, the overall jacket insulation. 1.6.9 SC and USC. This is not use cable. You don't pronounce it use. It's underground service entrance, USE. So call it service entrance or underground service entrance. It's type SE or type USE cable. You'll find information for the use of service entrance cable and underground service entrance cable in NEC Article 338. Type SE cable is for above ground installations only. This is highlighted. It says type USE cable is for exterior installation, including direct burial in the earth. That's what the U is for, underground service entrance. To find the temperature rating of type SE or USE cable, look on the outside surface of the cable for the cable type designation, then consider the following. If the type of designation for the conductor is marked on the outside surface of the cable, temperature rating of the cable corresponds to the rating of the individual conductors. If the type of designation is not on the outside surface of the cable, temperature rating of the cable is 75 degrees Celsius. Here's a highlight. It says, when used as a service entrance cable, type SE cable must be installed as specified in Article 230. Article 230 is about services. So here's an example of type SE cable. The neutral is bare. These bare conductors wrapped around the outside, that's the neutral. So you have 2 hots and a bare neutral. Then there's fiberglass tape, and then there's the jacket. Type USE cable is sizes from 4/0 gauge and smaller, with all conductors insulated, is suitable for all underground uses allowed by the NEC for type UF cable. Type USC cable may consist of either single conductors or a multi-conductor assembly provided with moisture-resistant covering, but it's not required to have a flame retardant covering. This type of cable may have a bare copper conductor cabled with the assembly. Type USC single, parallel, or cabled conductor assemblies recognized for underground use may have a bare copper concentric conductor applied. These construction do not require an outer overall covering. Okay, let me move on. Instrumentation control wiring. Instrumentation control wiring links the field sensing, controlling, printout, and operating devices that form an electronic instrumentation control system. The style and size of instrumentation control wiring must be matched to a specific job. Instrumentation control wiring usually has 2 or more insulated conductor wires. These wires may also have a shield and a train. An outer layer called a jacket protects the wiring. Instrumentation conductor wires come in pairs. The number of pairs in a multi-conductor cable depends on the size of the wire. A multi-pair cable typically has 12, 24, or 36 pairs of conductors. More information on the application of instrumentation control wiring can be found in Articles 722, 724, and 725. So here's the outer jacket. Here's a drain wire and a shield. This one's non-shielded, just has 2 conductors. Doesn't have, there's a shielded and unshielded. 1.7.1 Shields. Shields are used on instrumentation control wiring to protect electrical signals in the conductors. Without the shield, electrical noise may disrupt the signals. It may cause false indications and improper operation of control devices. Shields are usually made of aluminum foil bonded to a plastic film. Oh, they're about to talk about it. I was going to say something. All right. It's 1.7.2 shield drains. We only terminate the drain at one end. A shield drain wire is a bare copper wire used in continuous contact with a specified grounding terminal. A shield drain allows connection of all the instruments within a loop to a common grounding point. Always refer to the loop diagram to determine whether the shield is to be terminated. Figure 20 shows the shield and shield drain on instrumentation control wiring. Like I say, here's the shield and the shield drain. Here's the cable shield drain. Most of the time, we will only terminate the shield drains at one end, and it's usually done at the control cabinet. So you bring all of these field wiring communication cables into the panel, and they're for low voltage communication purposes, and all of the drains are made up and taken to ground at the panel. In the field, you wrap them on themselves, and then you put some electrical tape around it to keep it isolated from touching anything else. This protects the cables from interference with induced currents from stray voltages. If there's something operating at 120 volts near a communication cable or an instrumentation cable, it can induce current in that instrumentation cable that can be interpreted as a command or a communication that is false. So this protects the cable from getting those false messages by grounding it only at one end. If we were to ground it at both ends, then you would have fault currents or induced voltages or currents running in both directions, and it would again simulate a false message. So that's why they only ground it at one end, so that all the stray currents go toward that one point and they don't get mistaken for a message. This is a highlight. It says typically the shielding in instrumentation circuits is only grounded at one end of the conductor. The purpose of this is to drain induced charges to ground, but not allow a circulating path for the flow of induced current. If the ground is not to be connected at the end of the wire you are installing, do not remove the ground wire. Fold it back and tape it to the cable. This is called floating the ground. 1.7.3 jackets. A plastic jacket covers and protects the components within the wire. PE and PVC jackets are the most common. Some jackets have a nylon ripcord to cut the outer insulation along the cable, which allows the jacket to be peeled back without the use of a knife or cable cutter. This eliminates nicking of the conductor insulation when preparing for termination. So here's your section 1 review. Again, I'll let you go over those and find the answers. If your instructor wants you to answer these and hand them in, do that. If you have any trouble finding the answers, message me or put a comment below the video, and we'll find the right answer. I'll see you on the next